Professor Felix Otto from Bonn. He will speak on optimal error estimate in stochastic homogenization. Thank you very much.
Thank you for the invitation to this conference. So this is joint work with Antoine Gloria, who did his PhD with Claude Lebris, and then was a year postdoc in Bonn, and now is at INRIA in Lille. And the subject doesn't really fit with the subject of stochastic partial differential equations. It's more in the spirit of Nicolas Dill's talk yesterday about random data or random heterogeneities in otherwise deterministic partial differential equations. And so to set the stage, let me introduce kind of the simplest possible setup we have been looking at. So it's about homogenization of elliptic equations, and we look at discrete elliptic equations. So if you want elliptic equations on a d-dimensional lattice, and let me use the manual pointer. So you have sites which typically I will call x, and you have bonds or edges which typically I will call e, and on every edge you have a conductivity which varies from edge to edge, a positive conductivity, and you're looking at the related elliptic operator, so given by the symbol. You can either look at the operator itself, which would be this one, which turns into the usual 5-star Laplacian if the conductivities are constant, and but they're not constant, and so it's a weighted average of these differences over these 4 bonds and 2 space dimensions. Or you could look at the corresponding form, which well, it's kind of Dirichlet form with this weight here. So that's the elliptic equation. And now the assumptions on the stochastics we make are the simplest possible assumptions. So first of all, we assume that the equation is uniformly elliptic in the sense that all these conductivities are bounded below by a possibly small positive constant lambda, and that these conductivities are independent from bond to bond and identically distributed. And then it is well known since 30 years, about 30 years, that this elliptic equation, or let's say the solution operator or the resolvent equation, on large scales behaves like a homogeneous and deterministic and continuum equation, so characterized by constant deterministic effective coefficients, the homogenized coefficients. And so that is work on the one hand by Kozlov and by Papanikolaou and Varadan. I put the name of Kuhnemann here because he, I guess, was the first to treat the discrete case. These authors treated the continuum case. And another way of looking upon, of giving an interpretation to these homogenized coefficients might be the following. You look at the corresponding parabolic problem. So let's say you look at the corresponding parabolic Green's function. So you take initial data which correspond to 1 at a particular site, let's say 0 and 0 everywhere else, and then you let the parabolic equation run. So that defines the parabolic Green's function, or if you want the probability of a random walker, which jumps from side to side in this on this lattice, then you will find that after some time, this Green's function, which of course is somewhat is kind of a random function because it depends on the random coefficients, gets closer and closer to a deterministic Gaussian, which whose variance is given by the inverse of the homogenized coefficient. So in a certain sense, that makes a connection to the area of random walk and random environment. And in fact, as Jean-Dominique Deutschel told me, this parabolic result, especially if you want to have an almost sure parabolic result here of this homogenization type, does not follow from the previous theory, but requires some kind of different arguments. So, for instance, which can be found in this paper by Zidora, Vicius, and Snitman. And but perhaps I can come back to this a little bit later. Okay, so we were not interested in the in this problem of kind of speed of convergence, but in the problem of how to determine these homogenized coefficients. And so there is some easy intuition about how these homogenized coefficients are determined. So if you think a little bit in terms of electrostatic analogies, so conductivities are the inverses of resistances, and then it's very clear that in one space dimension, where in a certain sense these bonds are resistors, which are all aligned, that in this case, kind of the resistances should add up, so that the expected value of the resistance should be the homogenized resistance. So in fact, in one space dimensions, it's very easy to convince yourself that this is an exact formula. So in one space dimension, there's no problem at all to infer these homogenized coefficients from the underlying statistics. But in multiple space dimensions, so let's say in two space dimensions, it's already clear that this can't be as simple, because now you have a network, and if you send a current through, some of these bonds act like resistors in series, and some of these bonds act like resistors in parallel. And therefore, you know that in series you have to add the conductances. Sorry, if they are in parallel, you have to add the conductances. Otherwise, you have to add the resistances. So in general, you will expect homogenized coefficients which are kind of trapped between these two bounds. But you don't know much more on the specific value of these homogenized coefficients. So in general, there's no simple formula to go from this one-dimensional distribution function, which tells you the probability distribution of the conductances, to the homogenized coefficients, which, by the way, here in this very simple model are isotropic. So so that's kind of the issue I want to address. So from a very practical point of view, it's actually kind of intuitive how you would try to infer these homogenized coefficients. You would consider kind of a large sub-element of your lattice of a very large size L, so many sites, and you would impose kind of different potentials at the left and at the right end, and perhaps some periodic boundary conditions at the lateral end, and then you would compute the average current, because what the homogenized coefficient really does, it's a relation between the average potential gradient to the average current. And that would be a very practical approach to how to determine, at least in the limit when L goes to infinity, these homogenized coefficients. And but there is a very clean mathematical way of doing that, and that involves the so-called corrector field. So which is already an important notion in periodic homogenization, and plays an as important role in stochastic homogenization. So what's the corrector? The corrector field is something which is defined for a given direction in space, psi, which I always will denote psi. And essentially, it's characterized by two properties. It is such that if you add it, therefore it's a corrector, if you add it to the linear function with slope psi, it has to be a harmonic function, an aharmonic function, so it has to be an exact solution of this equation. So in a certain sense, it modifies the linear slope in such a way that it gives you an exact solution. And on the other hand, it never deviates too much from the slope in the sense that the gradient of theta has average 0 and is stationary, in the sense that if you shift the gradient by some shift zeta, the new function has exactly the same statistics as the old function. In fact, you would like to say that phi itself is stationary, and this, but this is kind of an open problem, or what I'm going to tell you about, in fact, shows that in dimensions larger than 2, you can also construct in such a way that phi itself is stationary. But up to now, in a certain sense, that's the way to define the corrector. Here is a numerical plot of how a corrector field looks like, and essentially looks like to the eye as kind of random field, white noise random field, which of course it is not in general. Okay, so with help of the corrector field, you can write down an exact formula for the homogenized coefficient. So you take the corrector field phi, and you look at the gradient of the solution of the equation, and you look at the energy density, which is this expression. This is statistically, this is a stationary scalar field, so it doesn't matter at which point you take the ensemble average. And the ensemble average exactly gives you the quadratic part of the homogenized coefficients, and since the homogenized coefficients are symmetric, it's the quadratic part which already characterizes these coefficients. So that's kind of, in a certain sense, the idealization of this representative volume concept, volume element concept, which I gave before. It gives you a very clear formula, but it is of little practical use, because in order to really evaluate this, I mean, if you want numerically find this coefficient, you would have to solve the corrector equation for every realization of the coefficients and also on the whole lattice. So it is not immediately of use, and therefore it has to be approximated. And so this, in a certain sense, brings one back to the idea of representative volume elements. And so essentially, you do the same as before, perhaps a little bit smarter. You introduce some artificial periodicity with period L, in the sense that you're saying the following: you take your random coefficient within this sublattice, and then you extend the random coefficients periodically. So that's what I indicate by AL. And then you solve the corresponding corrector problem with periodic boundary conditions. And then you take spatial averages over one periodic cell. So when you do that, of course, you make two types of errors. So the first error is that you've changed the statistics. You've gone from a completely uncorrelated independent statistics to correlations, because due to the periodic extension, of course, you're repeating the pattern and you have spatial correlation. So you make a systematic error because you've now working with the wrong statistics. And then you make a random error by replacing the ensemble average by a spatial average over your periodic cell. And in a certain sense, you want to have a good idea of both types of errors which you make. And the reason why this might be interesting to why this actually might be of practical interest to get an idea of the scaling of the behavior of these two errors is because that may tell you what a good numerical strategy actually is. Because in a certain sense, you have, of course, you can now look at n independent samples. When you're looking at the spatial average, you can do that n times for n independent samples. And now, in a certain sense, you have two parameters to play with. you have the system size, your artificial period L, and you have the number of samples. And if you increase the system size, you both decrease the systematic and the random error. But if you increase the number of samples, you just increase the decrease the random error. So it's not clear, in a certain sense, how you should distribute your computational degrees of freedom, rather doing many copies of a small system or going to a few large systems. So therefore, it's interesting to investigate these errors. So so that has been a quest for quite some time in the mathematics and applied mathematics literature. And there's one simplification which is always which is always done in the sense of replacing periodic boundary conditions by something which is analytically more tractable. And instead of introducing periodic boundary conditions, you modify the corrector equation by a so-called desorption term. So, so a small zero-order term, and the notation of t minus 1 comes from the random Walker interpretation of this partial differential equation, because in a certain sense it gives you the time scale after which your random Walker dies. And so therefore that's a good notation for this parameter, for this small number in front of the zero-order term. And then the idea is that if you adjust this parameter in such a way that t is proportional to L squared, so that here you have L minus 2, then looking at this equation is not much different from imposing periodic boundary conditions, in the sense that if you're interested in the solution of this problem, let's say here at the center, it will not see not much see, or only exponentially small effects of the edges which are away more than square root of t. So therefore, square root of t plays the same role at L, and therefore for t equal to L squared, this equation is seen as a good proxy for the periodic problem. And then if one allows oneself this simplification, the systematic error can be rewritten like this. It's in a certain sense the difference between the corrector problem with the zero-order term and without the zero-order term, the gradient squared, the expected value thereof. And also then it makes sense to, instead of doing a spatial average over a periodic cell, there is no periodic cell anymore, you do a spatial average over a length scale L by some smooth kernel WL. And then the random error, which is the difference between the spatial average and the ensemble average, can be re-expressed as the variance of the spatial average. So in a certain sense, we now have two clear error expressions. And what can we expect? So, so there's one simple type of analysis one can do in order to find out what to expect, and that is to look at the regime of small conductivity contrast. So at the case when kind of the bond conductivities only differ very little, so are very close to 1, meaning that the smallest possible value is very close to 1. And in this case, you can linearize in a certain sense in this small parameter, and you get exact formulas for these two errors, and you find out that the systematic error has this scaling which first follows the dimension and then has a crossover at 4 dimensions, and that stays fixed, frozen in at that dimension. And the random error really behaves like you would expect in the from the central limit theorem. The square scales like 1 over the volume of your box. And so clearly in kind of physical dimensions, you see that the random error dominates the systematic error, which indicates that in principle it makes sense to look at many samples instead of just one large sample. So the question is now, what if this can be proven? What if these estimates can be established rigorously when you don't assume small viscosity contrast? And in fact, we get almost the same result. So at least in dimensions larger than 2, we get exactly the same result. We get this, that the systematic error has exactly the behavior with the crossover at 4 dimensions, and we get that the random error exactly behaves like it should by the central limit theorem. In 2 dimensions, we acquire an additional logarithm in this cutoff parameter t, where the power of the logarithm depends on the viscosity ratio. So in that sense, we get the optimal the optimal results at least in dimensions larger than 2, even in the strongly nonlinear case when the conductivity ratio is large. So let me comment a little bit on previous work on these error estimates. So there's one quite old, but in a certain sense still unsurpassed error estimate, which by Urinsky, and he uses a kind of a very different, a much more stochastic approach than the approach we're using, but he gets somewhat suboptimal estimates. He essentially looks at the systematic error, so the difference between the, perhaps I should write down the 2 equations on the blackboard. So that's the modified corrector, and this is the original corrector equation. So for the systematic error, for the difference between the modified and the original corrector, he gets a decay in t, which should be this one here, and which is quite a bit smaller. In particular, he doesn't get any result in 2 dimensions. And but although he looks at the systematic error, his analysis really relies on a variance estimate, like you would for the random part of the error. And what he looks at is are variances of spatial averages of the corrector field. And for those variances, he gets this type of decay, which depends both on the parameter t, the kind of the parameter of the modified corrector equation, and on L, which is the size over which you average, and that should be the optimal behavior. He still gets a t-dependent behavior, and the way he gets the this this estimate is really by a probabilistic argument. So so he says his point of view is that the solution of this equation really can be written down with help of random Walker representation. So so as a path integral, and based on this path integral, or on this random Walker representation, you get a decomposition of this function into a sum over edge sets. So for every edge set, so here is a subset of the edges, he gets one element, and they all sum up to this potential. And the idea is, of course, to just take the contribution which comes in the random Walker representation, which comes from the random Walker whose image is given by the set up to some time t. And so then automatically he knows that this part of the sum just depends on the conductivities on these edges. But on the other hand, he knows, or by some elliptic estimate, he knows that typically this will be a thin set. This will be a 2-dimensional set because it's the image of a random walk, so that typically has dimension 2. And if you're in dimension 3 or higher, this is a small set, and therefore your potential only, in a certain sense, only minimally depends on this thin set, and therefore he gets an estimate. So that's the idea, that's the main idea of his proof. And so this is one work which inspired us, and then there is an unpublished work by Nadav and Spencer, which is in a certain sense from which we took more ideas than from the work of Urinsky, which is which in a certain sense looks at a different problem. It looks at the original homogenization error, and one way of presenting it is the following. So their working horse is really a spectral gap estimate. So they say if you have a random variable which depends on these independent conductivities, then in a certain sense the variance of this random variable can be estimated by this expectation of the gradient of this infinite dimensional gradient with respect to the to how this random variable depends on the conductivities. So that's a spectral gap estimate or a Poincaré estimate with mean value 0 in this high dimensional space, and that's their starting point. And now they look at this type of elliptic equation with random coefficients a and let's say deterministic right-hand side f. And the quantity they want to monitor is like a little bit like we do the energy density, which is this Dirichlet integral. So that plays the role of your random variable. And then it's very nice because of the special features of the energy density. The way it depends on the value of the coefficients is very local. It's just the gradient at that coefficient squared. So now you see if you plug this here in there, you get the gradient to the power 4. So you get some strong nonlinearity. And then they bring up something which is well known in linear elliptic regularity theory, which is Mayer's estimate, which tells you that even in an equation with just uniformly elliptic, but no continuity, no modulus of continuity on the coefficients, just uniform ellipticity, there is an exponent which is slightly larger than p, slightly larger than 2, so that you have kind of maximal regularity in this LP norm. And in fact, somewhat closer inspection of the way Mayer's estimate is derived, you find that if the kind of viscosity contrast goes to 0, this number here goes to infinity. So the range of exponents for which you have maximal regularity gets larger and larger as the viscosity contrast goes to 0. So therefore they say, well, provided the ellipticity contrast is sufficiently small, not infinitesimal, but sufficiently small in a way which can be characterized, we have the optimal regularity on the L4 level. And now that is exactly what you can plug in here, and then you get that the variance of the energy density is estimated by the L4 norm of the right-hand side, and that's the estimate which is kind of optimal in terms of scaling. So, so that shows that with a bit more of kind of elliptic theory, at least in the case of small ellipticity ratio, you can get further and you can get estimates which scale optimally. So that's a little bit what we got inspired by. And now perhaps I can. I still have half an hour, right? Yeah, so then I would like to continue on the blackboard to give you kind of an idea of the main idea of the proof. So I should give a signal to the, thank you. So in a certain sense, the main ingredient for our proof is the following: is a moment estimate on the corrective field. So what we prove is that for any exponent, the stochastic moments of the corrective field, so it doesn't matter at which point I evaluate because of stationarity, at least of the approximate corrective field, is estimated by some logarithm of t in the two-dimensional case, and is bounded independently of t and with a constant which depends on q. So I should, I should give this another name. So this depends on q and on lambda, and the constant depends on q and on lambda, and here it depends on q and lambda, and no dependence on t. So in a certain sense, at least in dimensions larger than 2, we show that this corrector field has bounded moments independently of this cutoff here. So in particular, you can go to the limit and you recover, you get kind of this, as a byproduct, this result that you can indeed construct a corrector field which itself is stationary. Not just the gradient is stationary, but the corrector field is stationary, which in a certain sense is also this type of boundedness of the corrector field is also at the origin of Snitman's work on the invariance principle for the random walk in a random environment, because what he needs to do there in order to show that is to show that the corrector field grows sublinearly if it's fixed to be 0 at the origin. So in a certain sense, this is then a much stronger result, and it's really on what our analysis relies on. So now I would like to give you an idea of how to prove this, this estimate, at least in the case d larger than 2. And let's start in a very naive way. So let me set t equal to 0. For the dimensions d larger than 2, that doesn't matter. So we're really looking at this equation. And let's say we were not very ambitious in the beginning, and we just wanted to estimate this quantity, the square of the field, at some point which doesn't matter. So let's say 0 or some other point. And then since at least on the level of the approximate corrector field, we can always normalize by this condition. This here is equal to the variance of phi. And now we can use this spectral gap estimate, which tells us that, at least roughly speaking, I mean, that's not true. One has to modify the spectral gap estimate a little bit to treat general coefficients, but let me sweep this detail under the rug. This is estimated by the way the corrector field, let's say at 0, depends on variations of the conductivity at edge E squared and the expected value, and then the sum over all edges. So you're somewhere here at point 0 on your lattice, and here is your edge E, and you're varying the conductivity here, and you want to know what is the influence on the value of phi at this point. And not surprisingly, there is a formula for this which involves the Green's function. So this is given by minus the gradient of the Green's function anchored at 0, gradient of the Green's function, or the second variable at this edge, times gradient phi of E plus psi. So that is the formula which you get. And now if you plug in this formula, and you're being very brutal in terms of estimates, so let me continue here, you would get the sum. Now you take the sup over all coefficients of the gradient of the Green's function squared. We have the square here, times the expected value of the gradient of phi squared plus 1. Let's say this has length 1. So that's the estimate which you would get. And by stationarity, it doesn't matter that I evaluate this gradient at an edge E. I could as well evaluate it at edge 0. And this quantity scales like the homogenized coefficient itself, so that's at most of order 1. So what you're left with is just the sum over all edges, sup over A, grad G 0A. So in a certain sense, now the big question is this sum here finite? So you would like to say that the gradient of the Green's function decays like it should in the constant coefficient case, which is d minus 1, the distance to the origin, so the distance of the edge to the origin to the power d minus 1. But of course, this is not true uniformly in the coefficient. So therefore, this estimate, which in principle, if this estimate was right, then you would be done. And it would also show you that the two-dimensional case is just the critical case, because you make the calculation. That's exactly when this integral logarithmically diverges. But the problem is really nonlinear. I mean, you don't look at low contrast viscosities, conductivities, but you look at large conductivity contrasts, and therefore you really need a kind of a different approach here. So then you kind of think again about what do you know from elliptic regularity theory and Harnack inequalities and that type of thing. So because you do know a couple of things which are uniform in the coefficients. So for instance, you know that the Green's function itself uniformly in the coefficients has the optimal decay, which of course is d minus 2 in dimensions d larger than 2. And if you refine a little bit kind of this theory, I mean, you use the Harnack estimate once more, you know that there is an exponent strictly larger than 0, so that also the gradient of the Green's function in the second variable is estimated by something which decays a little bit better, by some epsilon or by some gamma better. And already if you use this here in the Buff inequality, it tells you that you're fine in dimensions d larger than 4, equal or larger than 4. So the kind of the difficulty really is in low dimensions, so it's in particular in dimensions 2 and 3. And where you cannot just give up most of this gradient. So you have to go back to what can you say uniformly in terms of the gradient, and there's always something which you can do fairly cheaply, which comes from Caccioppoli's estimate, which tells you that you can convert for an harmonic function, you can convert estimates on the function itself into estimates on the gradient, but those are averaged estimates on the gradient. So what that would give you is that on some dyadic annulus of between radius r and 2r, let's say, you look at the gradient of the Green's function, you square it, you take the average over the annulus, so you divide by its volume, rd, and then you take the square root, that this quantity decays the right way. So at least in a spatially averaged sense, the gradient behaves the right way. But in a certain sense, that is still not enough, because that would require, since you have a square here and you get the gradient square times the gradient of phi square, that would require to take out the sup of the gradient of phi, which is way much to expect. So what saves us is that, as what also Nadaf and Spencer realized, that you can improve this here a little bit. There exists an exponent. Sorry? D minus 1, optimal decay. So thanks to the average in space, you do get optimal decay in this average sense for this L2 average, and by Mayer's estimate, you even get it for an exponent which is slightly larger than 2. So that's what we have at our disposal. Optimal decay of the gradient uniformly, so I should add the sup over, so this is uniform in the coefficient. Uniformly in the coefficient, but only spatially averaged over dyadic annuli to a power which is somewhat a little bit larger than 2. Okay, so I guess I have the time to show you how from here and kind of this basic idea, you get the estimate. So there's a second ingredient which we need because it is no longer, so the fact that the square gradients are on average finite is no longer enough. And what in fact can be easily shown, I give you the argument in a second, is that higher powers of the gradient can be estimated by slightly lower powers of the potential itself. So of course this estimate for q equal to 0 turns into this estimate, but this estimate has the advantage that you control higher moments of the gradient at the expense of lower moments of the function, somewhat lower moments of the function itself. And so how do you get this? So this is so that's the second ingredient. So what's the argument of for the second ingredient? So first of all, since you're in the discrete case, gradients are always estimated by the function itself. So what you really need is just this estimate. So where you say you can multiply the gradient square with phi q, and then this here is effectively bounded. And that is again a Cacciopoli type argument. So you test the equation with a nonlinear power of the solution. So this equation, if we do this, we get the divergence of this function we multiply with a grad phi plus xi plus the term we want, q phi to the power q grad phi a grad phi plus xi is equal to 0. And now if you take the expected average of this equation, you can pass it under the divergence. And then by stationarity, this is constant. So this is equal to 0. So what you get is phi q grad phi a grad phi plus xi is equal to 0. And now by ellipticity, this turns into phi q grad phi square. Lambda is estimated by phi q grad phi. And then you do one Cauchy-Schwarz here, and you get the inequality. So so that's an easy part. Okay, so now how do we get from this inequality and that inequality to the estimate? So we start out with some exponent which is fairly large. I'm going to adjust it in a second, and we look at the variance of this high power of phi. So this is, of course, phi to an even higher power minus this quantity here. So we see this as an estimation of this, essentially, up to a lower order term. And we use the spectral gap estimate on this quantity here. So we get the derivative with respect to an edge of phi n squared. And now by, let's say, phi n 0. So now by the previous calculation, this gives n phi 0 n minus 1 minus gradient g 0 e gradient phi e plus psi. And now we have to estimate this, this quantity there. Okay, so in a certain sense, the idea now is that we want to put Mayer's coefficient on the gradient of the Green's function. We already have a square here, so we are allowed to put the exponent p over 2 onto this part, and then the dual exponent onto this part, which I pre-computed. Because that will take me too long. So this is p over p minus 2. So if we carry this out, we get the sum over e, phi 0 to the power n minus 1 times p over 2 times grad g 0 e to the power p times 2 over p and grad phi e to the power p over p minus 2, p minus 2 over p plus 1. Okay, now we have a power on the gradient of the Green's function we can afford, but we have a, if p is close to 2, an extremely high power on the gradient of phi itself. But that one we can reduce a little bit with this estimate 2 here. So the idea is to choose the n. So first of all, by 2. This is estimated by phi to the power p over p minus 2 minus 2. And now the idea is to choose the n so large that this here is n. P over p minus 2 is equal to n, which means that n is equal to 2 over p minus 2, or p is equal to 2 times n plus 1 over n. And so with these with this choice, let me write it down again, what we have. We get the sum over all e's, phi 0 to the power 2 n minus 1 times n plus 1 over n, gradient g 0 e to the power p n over n plus 1 times phi to the power 2n over 1 over n plus 1. So that's the, if we plug in the value of p, that's what we get. And now we want to bring into play this estimate on the pth power of the gradient of the Green's function. What is a nuisance still is kind of this exponent here. So what we do first is we decompose the sum into dyadic annuli, and then we use Hölder's inequality over the dyadic elements. So let me do this. Let me try to do this in one step, or well, why not two? So those are the dyadic parts. Phi 0 to n minus 1 n plus 1 over n, gradient g 0 e to the power p, n over n plus 1, times this here really lives outside of the sum, 1 over n plus 1. So now we do one Hölder with respect to this inner sum here to get rid of this exponent. Let me keep this one here. Oops. So we get the sum over the dyadic annuli, the volume of one of these dyadic annuli to the dual power here, which is 1 over n plus 1, times the q k plus 1, phi 0, q n minus 1, n plus 1 over n, grad g 0 e to the power p to the power n over n plus 1 times this factor here. Okay, now you see, now this has the advantage that we can pull this sum here and then use the, well, let me write this here. So first comes the expected value, then comes phi 0 to the power 2 n minus 1 n plus 1 over n. Then comes the sum over 1 annulus of the pth power of the gradient of the Green's function. And then comes this factor here. 1 over n plus 1. And now we have the estimate still here of this expression here. So this is estimated by the volume of the annulus times the behavior of the Green's, the gradient of the Green's function. So d minus 1 times p, and there is still the power n plus 1, n over n plus 1. Okay, so now if we collect these terms, we get that this is the sum k 1 to infinity, 2k. So d over n, d times 1 over n plus 1, and 2k d times n plus 1 gives you just 2kd, plus d minus 1 p times n over n plus 1. That's for the dyadic part. And then we're left with this thing here. So I can forget the 0. 2n minus 1 n plus 1 over n times 2n 1 over n plus 1. And now this turns out to be exactly with this definition of n what it's supposed to be. So this is equal to 2. So this here is equal to 2 minus d. So you exactly see that 2 dimensions is critical, also in this somewhat more complicated calculation. And this here is strictly less than n. So, and I probably forgot the power n over n plus 1. And if you use Jensen's inequality once here, you find that the product is estimated by phi 2n to n squared plus n minus 1 over n squared plus n, which is strictly less than 1. So, so that closes the inequality because, almost closes the inequality because you've estimated the 2nth moment of phi by the 2nth moment of phi to some power which is strictly less than 1. And therefore, you can absorb. And so essentially, you estimated the 2nth moment of phi by the nth moment of phi squared. And then you can iterate this downwards, and you get all the moments of phi, not just the ones which were sufficiently high to be compatible with Mayer's estimate. So that, in a certain sense, is I think the main idea of the proof. Can we, for a moment, go down with the projector again? Switch the projector on again. Thank you. So once one has this moment estimate, the other estimates essentially follow by similar arguments and estimates on the Green's function, as I've indicated. And this brings me to the end. Okay. So essentially, I've shown you kind of these slides here on the blackboard. So roughly speaking, as opposed to what Urinsky did, this is a proof which doesn't use much probability theory. In a certain sense, the only working ingredient is the spectral estimate, or a modification of the spectral estimate, which we use. But on the other hand, we use a lot of linear PDE analysis. And now there are, of course, a couple of natural questions which arise. So in a certain sense, we really were interested in the continuum problem, and we're confident that, in fact, we've started to write it up, that similar methods or the same ideas can extend, we'll also be able to treat the continuum case where kind of the relevant length scale is the decorrelation or the correlation length of the coefficients. So which in a certain sense in this discrete problem is equal to 1, which in the continuum problem can be set without loss of generality equal to 1, and that's the relevant quantity for the estimates. The question is whether in the two-dimensional case one can avoid the logarithm. So certainly not in the moment estimate. There it's optimal, not the power, but you have to have a logarithm in the 2D case. But in the final error estimates, at least by the heuristics, there shouldn't be a logarithm. So perhaps that can be avoided with some care. And then what, from the point of view of applications, what also would be interesting is to treat homogenization not of single equations, but of systems, like in elasticity. And but there it's doubtful that these ideas may help because, as you've seen, they rely heavily on the fact that the equation is scalar because we're using Harnack's inequality a lot, and it's not clear what can be done in systems in this case. Okay, so that's it.
Thank you. Any questions?
Urinsky was not using Harnack, right? So
Sorry?
Urinsky was not using Harnack. So his ideas may apply to the system.
He does use Harnack in the sense that he uses estimates on the Green's function.
Right, which
Sorry? Yeah, so he also has Harnack in there. It might be that he uses less subtle estimates on the Green's function, but I don't remember well enough to see whether it can be used for systems.
Any other questions or comments? If not, thank you again.